So, good morning everyone. My name is Chris Weckesser. I had the opportunity this semester to do some research under the direction of Professor Robert Driver. I also had assistance from Professor Douglas Tomlinson and Cameron Franchak from Dialogue. So to start off here, give a little bit of context about this huge, ugly sentence there. It starts off, as we all know, technology is rapidly evolving around us and changing everything around us. The construction industry is always in transition as it's trying to improve the efficiency of its projects, construction, the management, the design process, and the communication. One thing that has helped improve efficiency in the construction industry is BIM, or Building Information Modeling. I'm going to skip ahead a little to the next slide so I can describe a little bit about BIM, and then I'll come back and explain the rest of those points there. So BIM, it's a system that uses computer models to, I guess, replace traditional blueprints. Everyone has access to these models, and they're able to receive the information that they need from these models. The nice part is that everyone's pulling their information from the same source, so you can remove discrepancies of people not having the same information and stuff. Another interesting part about BIM is it associates information with the elements in the model. So all these things in here, it looks pretty overwhelming, there's a lot in there. Everything has information associated to it. For example, if you designed a door in BIM, BIM would know that it opens up and it has this radius of opening. So if you design something within that path, it would tell you there's an issue. BIM could also tell you how much the door costs, who the manufacturer was, at what stage of construction it comes in, and there's no limit to what kind of information you can associate to these elements. Now, forgetting the door for a second, there are many other construction elements in buildings that are being manually designed over and over, and this can be an inefficient use of time and resources. Standardization of these BIM elements can reduce time and resources. It's better to use a few set templates than thousands of different custom designs. It reduces the problems further down the road. So I guess this kind of brings us to what we did for the last semester. We wanted to explore, I guess, how to standardize other structural elements and what kind of potential there would be in standardizing them. We started off with embedded plates because they're supposed to be simple. That's what I thought until I started this. There's actually a lot that goes on behind these things. But in order to start standardizing embedded plates, we have to look at which properties are important for designing embedded plates and how these properties will affect the performance of the embedded plates and how they perform under various conditions. So you can see one here. It's been cast into the concrete already and has a beam attached to it. It's supporting it there. These ones look like upside down tables. You can see the studs there. They are what are going to anchor the embedded plate into the concrete. So the first objective was to identify which embedded plates are currently used in industry. This step wasn't necessary, but it helped us a lot because this was open-ended and it gave us, I guess, an idea of which designs are being used in industry and what the parameters for design were. It kind of gave us the lines to color with them. The next part was to learn how to design embedded plates according to CSA A23.3-14 Design of Concrete Standards. This was necessary so that we could design standards that were in accordance to Canadian concrete standards. Next would be to create a program that would use these standards to automatically create embedded plates and test them and see if they work in certain conditions or not. And finally, propose embedded plate standard designs for BIM implementation. Luckily, Robert Driver is very, very popular. He had a lot of contacts in industry, so we were able to reach out and we harassed a bunch of engineers in industry asking if they could give us some designs to work with. Dialogue came in clutch and they provided the drawings for NREF, DINT, and the new Northwest Building College. And within these drawings, we found approximately 60 embedded plate designs. Once we had these designs, we recorded them into Excel, and we recorded them with properties that we considered were important for standardization, things that were key to embedded plates. These properties were the number of studs, the stud placements, stud dimensions, and the thickness of the plate. You can see a couple of designs here. One was from NREF and the other one was from the Northwest College. There are many others that were in there as well. Next was to learn how embedded plates performed under various conditions. To do this, I had to look into NXD of CSA, design of concrete structures. And this provided the equations and the information that was necessary to find out how these performed under various conditions. Within the book, it had about 7 modes of failure, considering the shear and the tensile forces. Some of these could be pulling out, break out of the concrete, there could be pry out, there could have been just complete shear failure. And we also had to consider how the shear and the tension interacted with each other. That changed things a little too. Next, using the designs that were provided from dialogue, we identified some patterns that were within those. And just as like a test, we created 200 embedded plate designs. These were basic square plates with 4 to 9 studs and just had varying stud placements within them. Next, a program or an algorithm was created in Excel. I want to throw algorithm in there, it makes me sound smarter than I really am. But created a program in Excel that would look at these 200 plates, and then what you do is you input your tensile force, the shear force, the distance to any concrete edges that the plate is in, and the compressive strength of the concrete. And it would look through them, and it would give you the best plate for the job. Now, to define that a little better, the best or the most efficient embedded plate was the one that passed all the tests. It didn't fail in any regards. It also passed the interaction test between the shear and the tensile force. And once it passed all that, we had to reduce the criteria down to 1. So we chose the embedded plate that had the least volume of steel. I figured that made sense. Next steps, because this was a lot already. Next steps are to create more embedded plate designs for Excel program to reference. We currently have 200 in the program. I want to create more variety, more plates for it to choose from to give us better results, maybe up to thousands, who knows how many we'll put in this thing. Next, create standards according to various loading conditions and distances to edges. And finally, explore more the opportunity of automated design. We have already a program that can select embedded plates that are best for you to use. It'd be cool to see what else this could be used for. So in conclusion, while investigating the potential here, we found that there was a lot of potential and that opportunities to increase efficiency were found. And finally, we need to conduct more research to be able to further exploit this potential. Thanks for your time. Thank you.
I'll take also 1 or 2 questions from Chris.
Yeah.
So currently the issue is that it's not standardized, so every single plate has to be custom made for each purpose.
Say that again?
Like it's not standardized right now, the design of plates. So every design is custom made for its purpose?
Pretty much. Every company has like when we looked in those drawings from Dialogue, there was about 60 different embedded plates. If you go to another company, you'll get more plates. And everyone has their different idea of what plates should be like and how they should work for certain loading conditions. And so it'd be easier to standardize that and say, look, these are, 50 embedded plates that will encompass, 80% of the loading conditions that you have. And so if everyone's using the same standards, the same plates, and these are already in BIM, we don't need to redesign them constantly, and it'll save money in the manufacturing process as well. They will be able to just create, a huge amount of plates according to these templates.
So this seems really specific to embedded plates, but could this be used for anything that's not standardized? Any other?
I guess that's the hopes. We started off with embedded plates, something that was simpler, something that was easier. And with this process that we've kind of developed here, we want to be able to expand this to other construction elements as well. And that's a whole other can of worms. That's a lot of other things to look into.
Thank you.
Any other questions?
I just have a quick one more just about BIM in general. What's the average like on a major construction project using like a BIM's process and not using? What is the savings in
So I guess it
time and
depends.
cost?
Oh, what are the savings? I know it varies, because BIM is more than just a model, it's a whole system. You have to change the way you think, the way that you access information for other people involved in the project. In Canada, we've been a little slower with implementing BIM. We've been resistant to change. It is being implemented. And if the company fully embraces BIM and puts in all that effort up front, there has been savings in time. If they're a little a little hesitant about it, sometimes it wouldn't even help at all. It wouldn't reduce time. I know in the UK, it's embraced a little more. It's more common practice, and it's even required in some projects because it allows for the owner to see what's going on constantly, and it allows for better communication and better project delivery. Yeah.
When you came up with those 200 different designs, you went through a manual, right? You went through the plans, and then you
Yeah.
picked the dimensions. Is there any other way that you're aware of to collect that information?
So it's been a work in progress trying to figure out like how we could design an embedded plate according to loading conditions. The only idea that I could think of this semester was putting as many potential plans in there and then have it reference those. With creating those plans, we looked at the drawings, we saw kind of what parameters they had for external spacing or spacing between the studs, and we tried to work within those parameters. As for other methods, I guess part of the problem with this research was it was incredibly open-ended. There was endless opportunities and there's endless options. We went down so many dead ends and had to come back. And so I'm sure there are plenty of other ways to do this.
Because I'm aware of laser scanning, where they scan the entire building from the inside, and they base BIM, they develop that based on the laser scans rather than actually looking at the design drawings manually going through them. So that could be something.
That's kind of cool actually. We could work in accordance with them. They could scan like the beams and the columns and automatically generate embedded plates for those connections given the building that was
So
scanned.
that way the whole process would be fully automated.
Yeah. And they would take me out of a job later on. Kind of scary.
So I'd like to thank Chris again, and we'll have to move on with the sake of time. Thank you.